Welcome to StableSword channel. Today we're discussing a famous riddle called n coins in a row, sometimes also referred to as pots of gold. We'll present three different solutions to it. The first one relies on nothing more than just some logical reasoning. No computer science background is required. The second one is a recursive function that uses memorization to speed things up, yet it still runs in order n squared running time. And saving the best for last, the third algorithm will find an optimal solution in linear time. N coins in a row is a game that's defined as follows. Some number of coins of various denominations are arranged in a line. Two players, let's call them Alice and Bob, take turns at removing a coin at either end of the line. They are free to choose which end of the line to take a coin from, but taking a coin from the middle is not allowed. The winner of the game is the player who collects the most amount of money. As you suspect, simply taking the biggest coin that's immediately available isn't always the best strategy. In this example, if Alice were to start by picking the last coin, which is the larger of the two immediately available coins, then Bob would be able to take the 9 coin and go on to win the game. Peter Winkler, in his book Mathematical Puzzles, describes a simple strategy that is guaranteed to work, but only if the number of coins is even. Alice, being the first player to make a move, just needs to sum up odd coins and compare it to the sum of even coins. If the sum of odd coins is greater, then she starts the game with the first coin and keeps on taking the odd numbered coins. Otherwise, she takes the last coin and keeps on taking the even numbered coins. This is possible to do because Alice has a choice at the start of the game to either pick the first coin, which is odd, or the last coin, which is even. Once she picks up the coin of her choice, Bob is always faced with opposite parity coins at both ends. So no matter which end Bob takes a coin from, Alice can pick up a coin from the same end and will be guaranteed not to lose the game. Of course, this works only if the number of coins is even. Moreover, this isn't an optimal solution in the sense that Alice does not necessarily collect the most amount of money. This is where the second solution comes in that uses recursion. For Alice to decide whether to take the left coin or the right coin, she needs to calculate the maximum profit that could be collected in each case. Let's call possibility A when Alice takes the left coin and possibility B when Alice takes the right coin. For possibility A, we remove the left coin from the game. We know that Bob would then take his coin, which could be on either end, spurring off two more possible ways that the game could be played. Since Bob is playing optimally, he will surely leave Alice with the worst one. So we take the minimum of those two possible outcomes and add it to the value of the left coin. Of course, we do the same thing for possibility B, except we adjust the index values L and R to account for our initial choice of taking the right coin. Finally, the function returns the max of A and B, meaning the better choice. This is the same function, but to improve performance, we add memorization, which is nothing more than a hash table that stores previously calculated solutions. Since index L could be anywhere from 1 to n, and index R could also be anywhere from 1 to n, you'd end up storing n squared possible combinations. Hence, the algorithm runs in order n squared time complexity. As promised, let's get to the third approach that finds an optimal solution in linear time. It was discovered by a Polish computer scientist, Tomasz Iziaszek, in 2010, and it's based on two observations. The first is that if you have the biggest coin in the whole sequence at either edge, then taking it is an optimal move. In other words, if the biggest coin is available to be picked up, you can just take it and not worry about whatever the sequence of other coins there is in the middle. For example, if the sequence is 3, 1, 1, 2, since 3 is the biggest coin in the sequence, you can readily pick it up, and that is guaranteed to be the most optimal move. Think of it this way. The worst that could happen is that you leave the second largest coin available to be picked up by your opponent, which is okay since you got the better of the exchange. The second observation is that whenever you have three coins, let's call them X, M, and Y, such that the middle coin M is bigger than or equal to both X and Y, then these three coins could be fused together and treated as if it's a single coin. The value of that fused coin would be X minus M plus Y. Here's a more involved example of applying the fusion rule. We find three coins where the middle one is greater than the other two and fuse them into one, and keep on repeating this until no such three coins could be found. The sequence that we end up with will be shorter and typically bitonic, which means the sequence starts off high, decreases towards the middle, and then increases back up again. Alternatively, the new sequence will be either increasing or decreasing throughout the whole length. Either way, we end up with the biggest value at one of the ends. So now, making use of the first observation, when deciding whether to take a coin from the left or from the right, we can just compare them to each other and know immediately which direction to go in. You can find a formal proof that these rules hold in Tomasz Izjaszyk's paper linked in the description. Applying the fusion rule is an order and operation that could be performed using a stack. Here's an actual implementation for those who are interested. We simply iterate through the coins array, pushing each coin onto a stack, and then check if the top three coins could be fused into one. So there you have it. N coins in a row game solved in linear time. For the full source code, please see the link in the description. I hope you enjoyed this episode. If you did, please click that thumbs up button to help support this channel. Of course, if you have any questions or comments, please leave them in the comment section below. Thank you for watching.